Welcome to Quality Assurance and Calibration Methods. So we'll get into what exactly quality assurance is in a minute, but first let's talk about why it's important. So suppose you took a sample and you split it up into a whole bunch of different parts and you gave it to a bunch of different labs and you had each one of them perform the same analysis on it. Do you think you'd get exactly the same results back from each of them? Probably not. So somebody's actually done this, and they sent out the sample to over 180 different accredited labs, and within those 180, there were 9 national labs. So within the national labs, in the certified range, just about all of the national labs got a value that, within the confidence interval, was within that certified range. Now, at these other accredited labs, you can see there's this huge variation. Some of them had a value that's far too low. On the scale on the side here, it ranges from 31 up to 91, where the certified range is really between about 61 and 64. So a lot of these, not only are the error bars much larger here, but the values are spread much more than they were over here with the national labs. And again, these are just the accredited labs. So there's this big variation here in the values that came back. So it's really important when you're performing some analysis to do so in exactly the same manner every time. Because you can see that it is possible from these national labs to get values that are very close to the true or the accepted value. But it's also possible, if you're not quite as careful, to get values that are skewed. All right, so there's always some uncertainty in our measurements, but we want to ensure that our measurements are as precise and accurate as possible. So quality assurance, then, is the systematic monitoring and evaluation of aspects of a project or facility or some service to ensure that standards of quality are met. Now, suppose that you're making spaghetti sauce for a few friends. You can taste the sauce, you can add some seasoning, you can taste it again, and so on. But if you're making spaghetti sauce in a factory that makes 1,000 jars of sauce each day, you can no longer taste each jar. So you select, say, 3 jars each day, spread out in time, and you taste just those 3. If they taste okay, then you assume that the other 997 are okay. However, some of the rest that you've assumed were okay will fall outside of acceptable limits. So is it worth testing more? Well, if the number of bad jars is only 100 per year, it's not worth testing a 4th jar each day, because that's 365 additional jars a year, and that's more than the number of bad jars. In other words, you'll waste 265 more jars by testing. It's better to just pay 100 refunds and be done with it. So one goal of quality assurance, or QA, is to ensure that the results meet the customer's needs. For example, if you manufacture a drug whose dose is just under the lethal dose, you need to be far more careful than if you're manufacturing spaghetti sauce, where the worst consequence is that you pay for a refund. We're assuming here that you're not getting sick off of the spaghetti sauce, just that you have sort of a bad mix of ingredients in there where it just doesn't taste good. Now, a bathroom scale with an uncertainty of plus or minus 1 pound is probably acceptable, whereas a pill containing 2 milligrams of active ingredient with an uncertainty of plus or minus 1 milligram is probably unacceptable. Now, part of the reason for this is that for your weight, plus or minus 1 pound is, depending on your weight, roughly 1% of your weight. But for the pill, plus or minus 1 milligram is plus or minus 50%. That's a very large percentage change. Also remember, if the scale gets your weight wrong, there's not really any consequence to it. You just think that you are the wrong weight, but it's not going to hurt you in some way. Whereas with the pill, it could significantly hurt you. So the consequences there are likely significantly higher. Now, as chemists, our products are raw data, treated data, and results. For the raw data, these are things like individual values of a measured quantity. For example, the volume from a burette. There's treated data, and these are things like concentrations or amounts found by applying a calibration procedure to the raw data. And then there are results. These are what we ultimately report, such as the mean, the standard deviation, and confidence interval. And thus, it's important to write clear, concise use objectives for data and for results. And you can then write specifications stating how good the results need to be and what precautions are required for the analytical procedure. For example, how should samples be taken and how many are needed? What special precautions are required to protect the samples to prevent degradation before you perform your analysis? And then within practical constraints, such as cost, time, and available material, what level of accuracy and precision will satisfy the use objectives? You also need to know what rate of false positives or false negatives is acceptable. This is probably higher for something like spaghetti sauce and lower for something like pharmaceuticals. For drinking water, a false negative, certifying that contaminated water is safe, are worse than false positives, that is, claiming that safe water is contaminated. The worst thing that happens there is you're out the cost of cleaning up that water. For athletic drug testing, false positives, that is, identifying an athlete as doping, are worse than false negatives, missing an athlete who is doping. Now let's look at sampling. We need to ensure that we collect representative samples. That is, we need to collect a set of samples that is representative of the population as a whole. For example, let's look at these 4 cases. If we only take, say, 4 samples, but we have different distinct regions, as in this case, then we're missing 3 out of our 7 distinct regions. So something better would be case 2, where we take 1 sample from each of our 7 regions. Now, simply taking more samples, increasing the number of samples in our sample set, doesn't necessarily make things better. For example, if you just copy 1 and you now make 3 samples from each of those locations, you're still only sampling 4 out of those 7 regions. On the other hand, in case 4, now we're taking 3 samples from all 7 of our regions. Now granted, we're also taking 21 samples here, whereas we were only taking 7 up here. Now, in this case, if you actually know that there are distinct regions within the area that you're sampling from, you probably do want to take more than 1 sample from each region. And that way you can compare within that region those data points against each other. And you'll have some idea of what the true mean is for each of those regions. Also remember that analyte must be preserved after sampling until the analysis is complete. Now let's make a few definitions. Selectivity or specificity is being able to distinguish the analyte from other species in the sample. In other words, avoiding interference from things that you don't want to detect. Sensitivity is the capability of responding reliably and measurably to changes in analyte concentration. In other words, selectivity is whether or not your analysis responds to things other than the analyte. So the more selective it is, that means that the fewer interference there will be. And sensitivity is how much your analysis changes, or how much the signal changes, when you get a real change in your analyte concentration. Now, there are lots and lots of jobs in quality assurance and quality control. For many companies, this is extremely important that they have products that match whatever guidelines they have in place. Also bear in mind, these jobs typically pay pretty well because you need to have a trained chemist performing them. And so, if you're looking for a way to apply your chemistry degree to get a good job, then pay special attention to this chapter. So now let's turn to standard addition. In standard addition, known quantities of analyte are added to the unknown in order to determine the initial analyte concentration. Now, your analysis must have a linear response to the analyte concentration for this to work. Now, this is useful when there are matrix effects. So, what is a matrix? A matrix is everything in the unknown other than the analyte. In other words, the analyte's environment. As you change what else might be in the sample, what else might be around those molecules that you're actually looking to detect, as we change that environment, we might change the way in which those molecules interact with our instrument. For example, if you have, say, an organic compound and you put a metal in there, that metal may change the molar absorptivity at whatever wavelength you're using to detect that organic compound. So let's define matrix effect. A matrix effect is a change in the analyte signal caused by something in the matrix. That is, it might be that if you change the concentration of something that is not your analyte, that you change the signal that you get out. You change the apparent concentration of your analyte. So matrix effects are common when the sample is complex, as often happens with real-world samples. For example, river water. Something that's manufactured by humans, like a pharmaceutical drug, that probably only has a relatively small number of ingredients in it. It's got the active ingredient, it's got some filler, it's got a binding agent maybe, it's got something that might stabilize some of the compounds in it. That's probably about it. Whereas on the other hand, something like river water has lots and lots of different chemicals in there. And those concentrations might vary significantly from one sample to another, or from one river to another. So let's look at an example. If we measure the relative mass spectral peak area as a function of the amount of perchlorate that's present, well, if we've put that perchlorate into reagent water, in other words, deionized water or distilled water, then we'll get some curve. But if instead we put that perchlorate into something like groundwater that has other species in it, you can see there's a much, much lower curve here. Now, it's still relatively linear, but in this case, if we didn't correct for the fact that this matrix is groundwater, and we were comparing, say, this data point here against those data points, we would conclude that there's very, very little perchlorate in our sample. Now, the initial analyte concentration can be calculated like so. We take the concentration of analyte in initial solution divided by the concentration of the analyte plus the standard in final solution. That's going to be equal to the signal from our initial solution divided by the signal from our final solution. Now we can write that out more mathematically like so, where we have concentration of X in the initial solution divided by concentration of our standard in the final solution plus the concentration of X in the final solution. Now note here that S and X are the same chemical species, but we know the concentration of the standard that we added. We don't know the concentration of X that's in the final solution. What we really want to find is the concentration of X in the initial solution, but we need to account for the dilution of adding some additional volume of water, or whatever else the solvent might be. Anyways, this side is equal to our signal, symbolized with an I, our signal from the initial solution divided by the signal from the solution with the standard added to it. So we can then calculate the final concentrations of the analyte and the standard if we know the initial volume of the unknown, V naught, the volume of our standard added, V sub S, and the total volume, which is V naught plus V sub S. And we're going to symbolize that with V total. So the final concentration of X, our analyte, is equal to the initial concentration of our analyte, which we don't know yet, times the initial volume before mixing divided by the total volume. The concentration of our standard after mixing is equal to the concentration of our standard before mixing times the volume of our standard divided by the total volume. Now note here that the quotient in parentheses here, this guy and that guy, are called the dilution factor for the standard and for our analyte. So let's look at an example. When you actually go to plot this then, you'll get something like this, where you'll have your absorbance or whatever else your signal is on the vertical axis, and you'll have the concentration of added analyte on the bottom. So the concentration of the standard that you have added. So you take one data point here, where you haven't added any of your standard, and then you take a number of data points where you add successive amounts of your standard, and if we then get this nice linear curve, then we can simply extrapolate backwards and figure out where this curve intersects the x-axis. That then, it's going to give you a negative value. That's essentially how much would we have to remove from our initial sample with no standard added. How much of our analyte would we have to remove to get our signal down to 0? Now there's another technique we could use instead. We could instead use an internal standard. So an internal standard is a known amount of a compound that's not the analyte this time, that is added to the unknown. Now, this is useful for analyses in which the quantity of sample analyzed or the instrument response varies from run to run. For example, in gas chromatography, if the gas flow rate varies by just a few percent, a calibration curve is only useful under the conditions at which it was obtained. However, the relative response of the detector to the analyte and to a standard are likely to vary by the same percentage. Now, an internal standard is also useful if sample preparation causes some analyte to be lost. In this case, a known quantity of standard is added before any sample manipulation, and then the ratio of analyte to standard is constant because the same fraction is lost in any operation. So the response factor, symbolized with a capital F, is the ratio between the analyte signal and the standard signal for equal concentrations. That is, the area of the analyte signal divided by the concentration of the analyte is equal to our response factor, F, times the area of the standard signal divided by the concentration of the standard. And more mathematically, that's then A sub x divided by the concentration of x is equal to F times A sub s divided by the concentration of S, our standard. Note here that these concentrations of X and S are the concentrations after mixing. And again, with internal standards X and S, the analyte and the standard are not the same compound. With standard addition, X and S were the same compound. So now let's talk a little bit about efficient experimental design. Suppose we have three unknown solutions of acid, A, B, and C, and we want to obtain the concentration of acid in each one and the uncertainty in that concentration. Now we could titrate each solution once to obtain the concentration, but we wouldn't know the uncertainty then. We instead could titrate each solution 3 times to obtain the mean and standard deviation, but now we need to perform 9 different titrations. Instead, we can use fractional factorial experimental design to obtain the concentration and uncertainty in fewer than 9 titrations. So what does that mean? We know we've got our 3 different acids, A, B, and C. If we show here the volumes of each of those that we're going to take in any one sample, so we'll take, say, 2 milliliters of A, 2 milliliters of B, and 2 milliliters of C, and then we titrate that with our strong base, like sodium hydroxide. We measure out the volume that we need. We can calculate then the number of moles of our sodium hydroxide that we used. And instead of simply performing that a number of times, what we then do is alter the ratios between our volumes. So we go with, say, again, 2 milliliters of A, but now 3 milliliters of B, and only 1 milliliter of C. Or 3 milliliters of A, 1 of B, 2 of C, and so on. And we get varying volumes of sodium hydroxide that we need, so differing amounts of base that we need. And then using a computer, which I'm not going to explain exactly how to do this now, take a look at the book, it explains how to do it. Using a computer, we can then calculate the molarity of each of our 3 solutions. We can calculate a standard deviation, which gives us an uncertainty value. And you note that we only had to perform 5 titrations. So this is in fact even fewer titrations than if we had only performed 2 titrations on A, 2 titrations on B, and 2 titrations on C. And of course, 2 titrations is not going to give us a very good idea of the uncertainty there. So by using efficient experimental design, we can obtain the numbers that we're looking for, the concentrations and the uncertainties in those concentrations, without performing a huge number of analyses. And so computers can be very, very helpful to us. Now, of course, we could perform these calculations by hand, but as the number of trials we have increases, as the number of different acids we might have increases, doing this by hand becomes more and more cumbersome, and thus this is where computers really begin to help us out a lot. They can basically perform a lot of this type of work with very little input on our side. And that was quality assurance and calibration methods.